Yeah, very good afternoon, all of you. Today's session is about explainable AI, how we can use in students' academic performance prediction. So without any delay, let me share the screen for you. I hope you can see I'm playing from the show. The topic name is Explainable AI-based student performance prediction using machine learning. And me, Dr. Dibya Jyoti Bora, I'm the Dean of School of Computing Sciences, Dasam Kaziranga University, Jorhat, India. So in this presentation, we'll cover this. The roadmap is first, the need means understanding the importance of explainable artificial intelligence. Okay, then data, about the data set, exploring it. Then we'll go for the practical. Okay, that we use Python, and then we talk about the shape logic. That is the main part of this presentation. Okay, now first, we will discuss about transparency imperative, means why educators must look beyond the standard prediction accuracy. Now, the black box silence. By that black box, what does it mean? It means that you don't know exactly in detail about what's going on, right? You have the answers, you have the output, you know the results, but because what are the factors behind that results, you have no idea. So that is we call as black box. Now you know standard ML models like random forest, XGBoost, they prioritize the accuracy, but however they do not reveal why a student was flagged at tricks, right? So hard to trust predictions, hidden algorithmic biases, and no actionable feedback. Right. These are some kind of negatives, or you can say some kind of drawbacks with respect to this type of traditional ML models. So this fixer, you can see, this is a black box model. Inputs are coming, right? You are getting the output, but you have no idea what's going in there, how it is going on, how the parameters being evaluated, right? Features being given, what type of weightage, you have no idea on that. Now, in case of white box model, it is purely transparent. You know how why this result come, how these things coming like that. So the glass box solution. Explainable AI, we call it as XAI also. It bridges the gap between high accuracy and human understanding. It provides a receipt for every prediction. You get it? So earlier, the models, ML models are giving you the high accuracy, but the problem is that you may somewhat feel some kind of less confidence to trust on those results, because just mere getting the output is not going to help. You have to know that how these things are coming, why the result is like that, right? So in education, this means an AI does not just say student A will fail. It should say, rather, that student A is at risk because of low family support and high absences. So, if you say the student A will fail, this is not going to give you a detailed explanation, or you can say detailed understanding about the condition of the student, that why he is going to fail, why the result will be like that. You rather you have to get the means output like that the student is at risk because of low family support. Then we know that the family support is less and high absences, because of that high absences are happening. So if we focus on these two, maybe the student's performance will be better, and he might not get some bad marks, or he will not fail, right? That we call as a glass box solution, and that is brought by XAI. Clear? Now, pillars of XAI. Okay, I'm calling it educational XAI because here the problem statement we are taking is about or is regarding some trust issues in educational predictions, academic performance predictions. Okay, so the three pillars are trust. It ensures educators believe the model's logic before making interventions. So it ensures the educators that to believe that model's logic before making intervention. I mean, they know about the model's logic better. Then fairness, detecting if the AI is unfairly penalizing students based on demographics. So if some kind of biasness happens, then can also be detected. Then actionability, telling the teachers exactly which factor to address. Like in the earlier example, you have seen the less family support, high absent, right? So this type of XAI will help the teachers to understand which factor, either study time or health, to address. So trust, fairness, actionability are the three pillars of this educational XAI. Now for this experiment, we have taken UCI student performance dataset, easily available in the UCI. You can just type this, you will get this. Okay, I can show you just a minute. This is the dataset we are taking, and you see UC Irvine Machine Learning Repository predict student performance in secondary education. This is the dataset, and you can take this link I'm giving in the chat box for you in the comment. Okay, so that data set we are using here. Let's know about this data set. This data approach to then achievement in secondary education of two Portuguese schools. Data attributes include student grades, demographic, social and school related features, and it was collected by using school reports and questionnaire. Right. Two data sets provided regarding the performance in two distinct subjects, mathematics and Portuguese languages. Okay, let's come back to the slide. Okay, just a minute. So exploring UCI student performance dataset variables. Here we have feature category, example variables, data types, and priority. Academic is the feature category where we have the Z1, Z2, their grades and failures. Data type numeric, priority very high. Then feature category behavioral, study time, absences, and alcohol. These are coming under behavioral feature category, and these values are numeric and priority is high. Socioeconomic like middle, edu, fem size, these are categorical and medium, right? And obviously you have a question in your mind that what is this T? Let me show you here. You can see here, these are the variables of common features in the student performance dataset. Midu means so it's a mother's education. Okay, Midu means mother's education. Data type numeric, scale is 0, non, 1 is primary education, 2 is 5 to 9, 3 is secondary, 4 is higher education. Fedu mane, Fedu father's education, right? Same. Fem size mane means family size, right? Categories like LET less than or equal to 3, ZTT mane greater than. Got it? So these are the variables where the value type is the data type is numeric. Okay, come back to that. Then demographic is address, gender, these are binary, and priority is less. Feature distribution analysis dataset, the model analyzes 33 distinct features. Academic history remains the strongest predictor, but social factors provide the necessary context for intervention. 649 Portuguese course instances, 395 mathematics instances, 0 missing values. 649 Portuguese instances, 395 mathematics instances, 0 missing values, academic, social, and demographic. So academic is having very strong value here, like this one, and then social is also, and then demographic. Now the pipeline we use here, machine learning pipeline for building and training the student performance model. First, we do the loading and encoding part, right? Encoding is needed because category values we have to convert it to numerical so that we can apply the algorithms here. And algorithm we are using here is the random forest algorithm. This is a kind of ensemble technique and falling under begging, right? After that, we explain the result with the help of this our main part, that is explainable AI. And for that we are applying step layer, right? Then the teacher intervention. And we use Python for implementing these things. Okay, we have used Python. So first we use label encoder to convert the categorical text like school GP, MS into binary digits of the model. The target variable GT is converted into a binary classification problem like pass is greater than equal to 10, fail is less than 10. To import pandas at 3D from SQL line preprocessing, import label encoder. We have defined this, read this data, label encoder. Okay, so target the GT is greater than equal to 10. Then random forest, why we have taken? Because it can handle non-linear relationship between social variables like alcohol consumption and grades better than simple regression. So it can handle non-linear kind of relationship between different variables, here social variable and grades. So we have taken random forest, and it is one more thing. It is good because it can handle the overfitting, right, much better the way, because it is not static, it is not fixed, it takes the random much in a much you can know means brightest way, because whatever the values we are taking, whatever the features we are taking, that is also going to be random. So that's why its performance is always found better whenever this type of problem exists, like overfitting and these things, right? It can handle that better way. Then robustness, by using 100 plus decision trees, it reduces the risks of overfitting to outliers in the student data. So I just told you that it handles overfitting because we are taking more than 100 decision tree, then obviously it is going to deal with every points in a random way. So overfitting is not going, is no chance there, right? And performance typically accuracy ranges from 88 to 91 because it is random. Now every time you will get the different accuracy level. So that's why I'm writing like this. So 80% data we use for training, 20% for tele testing, and then balance class weights. After fitting, the model is a black box. We need chat to explain it, right? We have fit the data, right? Then after that, we have to use chat to know what's going on, right? So here we need explainability mechanics. We are going to use shape to calculate the future influence. So understanding shape values, the game theory approach. Shape means what exactly? It is shapely additive explanation. So I'm repeating again, shapely additive explanation. It views the prediction as a payout and features as players in a game. It calculates how much each player, as for example here, what say absence is contributed to the final score. Its formula is like this one. This one you can go through this. Okay, so this is the formula for this. Now this is what actually our algorithm means gives better result or better explanation. Now we have to know a bit better way that how it works. This is a game theory logic. SAP is based on a mathematical concept. We call it as a Shapley values. For this, we take an example, say four friends with the features absences, study time, age, and family support are working together to predict a grade. Now, SAFE calculates the payout for each friend by checking how accurate is the prediction with all four friends. How much does this change if we kick study time out of the group? Matlab, suppose if we don't consider the study time, then what is going to be the change in the prediction? Then how much does it change if the study time works only with the absences? So this time of different combinations are possible. By testing every possible combination, it ensures that the credit given to study time is mathematically fair and consistent. Global versus local shape allows you to see the world through two lenses. The local lens, the individual. Why did the AI give Alex an 84%? The force plot. Global lens, the big picture that is across the entire school. Why, which feature is generally the strongest? So means individual wise we can also go through right there. Just like here in this case, Alex we are taking, why Alex is getting 84%. This is a kind of force plot. And then summary plot is for that. Suppose we want to find out that which particular feature is contributing more or is the strongest one in terms of giving out the prediction. Why is this important? Without CHEP, the AI is just a black box. It gives you an answer, but you don't know if it is being biased or focusing on the wrong things. With CHEP, the AI becomes glass box. You can see that Alex is passing because of his hard work, study time, not just because of a lucky demographic trait, right? So this builds the trust between the educator and the technology. Mere getting the output is not going to happen. You should also know that is there any bias going on in the answer or in the analysis, or is there how comes the answer to be like this? If we don't consider these features, then what will happen? This type of questions queries comes to our mind. If we get the answer to this query, then only trust level increases. Right. So global feature importance, you can see there are different features, G2, absences, failures, study time, alcohol tones. For all of them, some set values are there. Right. So summary of which feature drives the model's logic across all features. And here you can see these values. And from there, we can find out that which one is the strongest one among all the features. So we have implemented CHAP using Python. For that, we have imported CHAP, hide that model. And then we use CHAP.tree explainer, right? Explainer.chap values xtest, then summary plot chap values 1, xtest. So the tree explainer is specifically optimized for ensemble trees, making it much faster than the generic kernel explainer. Chap values 1 refers to the explanation for the first class. The B-swarm plot, interpreting the chaos, that like red dots means high feature value, blue dots means low feature value. If red dots on the right, high values of that feature increase the passing probability. So red dots means high feature value, blue means low feature. So if red dots are in the right direction, this means high values of that feature increasing the passing probability. We'll see in the plot. Okay. Then individual analysis, like local explanation for particular students, why he failed, like that. That is force plot, of course, or local. Force plots provide a breakdown of a single prediction. It shows the tug of war between features. Red bars push the predictions higher and blue bars push the prediction lower. Then shape diagnosis, suppose high absences minus to 25%, low study time minus 15%. So minus means in a different way, means it is negatively impact. High Z1 grade means plus 10%, means it is positively impact. So predicted fail, 42% probability. Assign mandatory attendance support, ignore demographic factors as they had 0% impact. Then feature dependency plot, interaction analysis, dependency plot show how the set value, you know, just 1 minute, I need to pick up this call. So dependency plots show how the set value for a feature changes as its value increases and how it interacts with other features. Say thus absences Absences have a worse effect on the students with low study time. Okay, so like that, we can find out shape values for absences and the study time. So absences increases, then how the study time will be means impacting. So that is one concern. Okay, so that kind of feature dependency plots are required to analyze the result. Does absences have a worse effect on the students with low study time? For means for those who are going to less study time and they're also high absent in the class, then will it going to be affecting their results? So this type of things we can analyze here. Then ethics and strategy, mitigating the algorithmic bias, demographic variety, ensure the model does not favor urban students over rural ones based purely on locations. Feature selection, use shape to identify if address or gender are driving predictions and remove them if they create biases. And model auditing, like regularly check global values plots for illegal variables carrying too much weight. So the human in the loop, AI is an advisor only. XAI is not meant to replace the humans, means the human teachers, but to empower them with evidence. Final decisions on the student's intervention should always remain with human counselors only, like accountability, moral judgment, contextual empathy. You can see here, this is human-centered AI in the education. Okay. So artificial intelligence, human computer interaction, cognitive and learning sciences. So base objective tool visibility, exploration, understand the data. We can use pandas, heat maps, visibility high. Training for maximizing accuracy, we are using random forest. Visibility 0, that is black box. Correct. Explanation, extract logic, we are using shape, line, that is high, that is a glass box. Deployment, you use, after that, we go for Streamlit based some deployment, that is a dashboard. Say, okay, ultimate goal is to wrap this model into a dashboard like Streamlit, where a teacher can click on a student and instantly see their shape explanation. This turns complex maths into simple conversations, starter for academic support meetings. So why is explainability specifically important in the context of education compared to other fields? That question comes to your mind. First, in education, AI decisions affect the student features. A black box model might flag a student as a risk without saying why, which can lead to bias or ineffective intervention. XAI provides actionable insights. It tells the teacher exactly what to address, like attendance versus study habits, ensuring the intervention is ethical, transparent, and targeted. Right. So AI should not be a final judge, but a sophisticated compass for educational growth. See, according to some leading AI education researchers. So, conclusion, I can say that by combining random forest accuracy with shape interpretability, we create ethical, transparent, and high impact early warning system for student success. Any question if you have, you can ask. These are the sources where we use what we use for the image and the other things. Thank you. I hope it's clear. Uh, okay, then if you have any question, then you can ask me. In the YouTube also, you'll find this lecture. I will give the link of this asset in the comment section.